I can see people filtering in. I'm going to start around 5:32, just so you know, giving some people the chance to log in. Thanks for coming. Thanks again for coming. We'll get started in just 2 minutes after people have a chance to log in. Okay, it's 5:32, which is when I was asked to get started, giving people a couple minutes to get in, but hopefully we have most of the people here, so people won't miss the beginning if there are a few latecomers. So thanks so much for tuning in to listen to this webinar. I have also to thank the William H. Donner Foundation, who supports the climate lecture series and funded this presentation. And what I want to talk to you about today is a topic that's very near and dear to my heart, which is how the ocean is changing rapidly, but also how the ways we observe it are changing. And so I'll do my best to walk you through some of the exciting things that are happening in the world of oceanography as we observe our ocean and climate in a rapidly changing world. So, and Emily, please let me know if anything goes wrong with the presentation along the way. So I'm going to start by just telling you a little bit more about myself. My name is Jaime Palter, and I'm an associate professor at the Graduate School of Oceanography at the University of Rhode Island. I'm talking to you today from a hotel room in Woods Hole, Massachusetts. I drove over Aquidneck Island this morning to come here for a meeting about ocean circulation. So I was trained as a physical oceanographer. That means I study the physics of the ocean, its dynamics, how it moves, ocean circulation, how the ocean interacts with the atmosphere. But more and more, I've been using it to study the transport and uptake of carbon dioxide across the air-sea interface. And I've been doing so using lots of ocean robotics, like these sail drones pictured here. And I've heard that there's interest among this community in learning a little bit more about sail drones, so I will talk about them in a little bit. But I wanted to go back in time a little bit and think about how I got to this point of becoming an oceanographer and why I did it and what I wanted to learn and where we're at today with that. And so when I was an undergraduate, I always thought that my oceanography and other geoscience professors seemed to see into the future. They had this crystal ball where they knew what to expect from the Earth system. And I found that just fascinating. I think it really drove home in a dramatic way when one of my professors said with great certainty that if a Category 3 hurricane were to hit the city of New Orleans, Category 3 or higher, that the city would be underwater. And I thought it was a kind of bold and very categorical, as if he was sure of himself, projection into the future. And of course, he was tragically right. And I saw that a few years after I took the class when Hurricane Katrina decimated the city, displacing tens of thousands. And you know, we all saw the tragic consequences of Hurricane Katrina. And I realized at that moment that what I studied could be part of the community that kind of understood the risks that we were facing in the future, and then worked, be part of this growing chorus of voices that was sounding the warning bells and trying to work for something better. And so that's what got me started. And I have no regrets. I really love being an oceanographer and have been using it to study all kinds of phenomena of great interest for the present and the future. So returning to the present, and this is the climate change lecture. I don't think we can overstate how much the ocean is playing a role in our climate system and doing a tremendous service for us in the climate. We all are aware that the atmosphere is warming and that the surface of the Earth is warming about 1 degree Celsius. But what we don't realize is that atmospheric warming that we live in every day, it represents only about 10% of the heating that's been trapped by the climate system due to the buildup of greenhouse gases in our atmosphere. 90% of the heat that's been trapped by the Earth system is in the ocean. And without the ocean, the pace of climate change would be much, much faster on the surface of the Earth, because the oceans are so massive and have a high heat capacity, they really slow the pace of climate change, which is a tremendous help to us. And so ultimately, though, this climate service of absorbing so much of the heat comes with a consequence. Of course, the oceans are warming. And so this is the sea surface temperature trend over the last 40 years or so in degrees Celsius per decade. So the sea surface temperatures have risen sharply, even as the vast mass of ocean beneath it has risen in temperature much more slowly. And a question I get a lot from people who know that I study oceans and climate is that to understand why 1 degree Celsius matters so much in our climate system. It's like the difference between a warm spring day that we had last week and the 45-degree temperatures we had over the weekend can be 20 or 30 degrees Fahrenheit, and 1 degree Celsius is 1.8 degrees Fahrenheit. So how can that small change influence our daily life? And so NASA put together this wonderful graphic that I think really summarizes it very well. And it just shows how that we may not notice the shift in the average. Where we really feel things is at the extremes. So this is a curve of all the temperature anomalies over land in the Northern Hemisphere in summer. And it's shown here for 1951. And so what they did is they subtracted the average out from every location. So the center of this bell curve is at 0. It's 0 temperature anomaly. The far right-hand or red side of the graph shows those sweltering summer heat waves that even in 1951, we experienced that hottest week of summer. And the tail on the left shows those cool, crisp summer days and nights that we all experience from time to time, at an ever vanishing rate. And if I can get this animation to play, let's see. There we go. The normal curve will dance around, showing its change year by year. And in the 50s and 60s, it just dances around the mean. Nothing dramatic is changing. But as we approach the 1980s, you can slowly see the center of the distribution shifting right. Don't stop now. Okay, shifting right and moving towards warmer and warmer temperatures, and those warm extremes becoming ever more common. So this gray curve shows the temperature distribution and land Northern Hemisphere's temperature anomalies for summer in 1950s. And the colored curve shows the same for 2020. And what you can see is the center of that distribution moved over about 1 degree Celsius. But let's think about what happened at the tail. That what used to be the warmest week of summer, those sweltering summer days and nights that we experienced for a week or two over the whole summer, is now much, much more common, maybe the entire month of July or August. The far right-hand tails, the warmest, the hottest of the hot anomalies, are now off the graph. So temperatures we never previously experienced. And those cold anomalies that can be important for certain types of agriculture or for keeping all kinds of pests and weeds under control have vanished entirely. So we no longer have those same cool, crisp summer nights that we occasionally experienced in the past. And so this is how humans frequently experience climate change and feel it very acutely. The same can be said for animals in the ocean, our friends, our marine mammals, fish and shellfish in the ocean, which are very sensitive to marine heat waves. And even though the ocean is massive and has a high heat capacity, it also can have dramatic heat waves. A review paper by Oliver in 2021 showed these very well documented heat waves all over the world with serious ecological consequences. These ones near Australia, bleached coral reefs. There were mass seabird die-offs in northern Alaska. And then this one close to home in the Northwest Atlantic in 2012 had serious implications for the right whale, an endangered species. We think there's only about 300 individual whales left at this point. And so the right whales, under the influence of this very strong warming in the Northwest Atlantic shelf, migrated northwards towards the Gulf of St. Lawrence, where they were under tremendous stress from ship strikes and entanglements. And so some of my work looks at what ocean circulation changes lead to this kind of rapid warming. And in the Northwest Atlantic, we found my student, Afonso Gonçalves Neto, now alumnus, a wonderful student, and another alumnus from GSO, Joe Langan, and I studied the changes in the Gulf Stream, which precede the rapid warming of the Northwest Atlantic shelf. And what we found is that using satellite data, we could get a predictor, a crystal ball into the future that gave about a year of lead time predictability for the rising temperature on the Northwest Atlantic shelf, which should be of great interest to managers of fisheries, and endangered populations like this to try to help them project where these populations might go. And always interested in forming new collaborations around people that are interested in things of that nature. So this is some work that really looks at the ocean physics and how changes in circulation can drive changes in properties like temperature. And I wanted to emphasize that I'm happy to answer questions. We're a pretty small group, so please don't be shy to put any questions in the chat or Q&A. I'm not going to dwell too long on this result because I want to move on to more recent work, knowing especially your interest in sail drone. So just feel free to put those questions there. So I want to move on to the second climate service that the ocean plays for us, which is that it not only absorbs 90% of the heat that's been trapped in our climate system due to greenhouse gases, it also absorbs about a quarter of the carbon dioxide that humans emit each year. So without that CO2 would be in the atmosphere, creating ever more warming at the surface of our planet. This also has a consequence in that it causes acidification of our oceans. But let's put that aside for a second. And I want to show you a problem that I think a lot about, which is that I said the oceans absorb about a quarter of the CO2 humans emit each year, but that uptake is highly uncertain. In fact, our best methods for estimating it in recent years have diverged from one another, showing the knowledge gap that we have in understanding ocean carbon uptake. This is my friend and colleague, David Ho, tweeting about it. He's an active Twitterati and a great follow on climate issues and oceanography, if you're into that kind of thing. And he shows the spread between these different products is nearly the emissions of the US. And if we take a more conservative estimate of the uncertainty in our ocean CO2 uptake, it's still the size of about Germany's annual emissions. And so this uncertainty is really problematic. It's much too high for lots of things that we care about. We can't close a global carbon budget, which means we can't verify nationally reported emissions. The Washington Post recently had a story about how uncertain nationally reported emissions are as countries try more and more to fold CO2 uptake from reforestation efforts and subtract that off from their emissions. And there are all kinds of reporting errors and lags. Some years the countries don't report, countries even with very large emissions don't report their emissions on time. And then there's also just getting a baseline for our oceans year to year. So we know, like the planetary health report, right? So that we know where we're getting to if we are with our goal of reducing emissions. Sometimes the atmospheric CO2 concentration would level off, but in a year that the ocean might take up less CO2 or the land, then we would expect the atmospheric growth rate to rise faster. And so without a closed global carbon budget, we can't have good judgment about any of those things, verify nationally reported emissions, or understand exactly where we are in our quest to reduce emissions to zero, which is what's desperately needed to slow and eventually stop global warming. So why are things so uncertain? Well, really, as my colleague Judith Hawk said in a recent paper, that what we really need to close the ocean carbon sink and the global carbon budget is a game-changing increase in high-quality ocean CO2 observations. And so oceanographers are incredibly collaborative and generous with their data. So all of the CO2 measurements over all the ocean have been compiled into a single atlas called the Surface Ocean CO2 Atlas. And I'm showing the data here, the raw data. And it looks like actually we have great coverage, right? Look at all those data points all over the Atlantic and the North Atlantic. But I need to tell you that all of these data were collected over all years since the 1950s. And even still, vast regions, 1,000 by 1,000 kilometer blocks of the southern hemisphere oceans have never been observed. These data are collected by research vessels, by ships of opportunity like cruise ships that allow scientists to put CO2 sensors on them and maintain them, and by buoys that are left out in the ocean for a year or more and serviced from time to time, as shown in this photo. And so you might think this looks not so bad, but this is all data collected over all time since 1957. Any single year like this from 2018 has much, much bigger gaps. And so we're just really not observing the ocean well enough to close the global carbon budget. And if I were to show you, as I will in the next slide, all of the measurements for a single winter, and winter is a critical season for ocean carbon uptake when a lot of it occurs. This is the 2018 to 2019 ocean carbon measurements for the winter season, December to March in the Northern Hemisphere and June to September in the Southern Hemisphere. Almost none, even in our well-studied North Atlantic, right off the shores of the Narragansett Bay campus and the Woods Hole Oceanographic Institution. So I'm part of a growing team of people that want to solve this problem. And so we're trying, and you might not make out that there's a little squiggle of data here in the Gulf Stream region. And I'll just put it in another color, and then below that, way up for you to see that this squiggle was our efforts in 2019 with the sail drone platform. And so we collected that data, almost as much in that single mission as had been collected in the month of February overall time for the Gulf Stream carbon. And my great student, Sarah Nickford, wrote a paper about this data. So I'll tell you, we collected this data with a sail drone. It's shown here in the background. It is an uncrewed surface vehicle. That means there's no crew, or we used to call it unmanned, but being more egalitarian, we call it an uncrewed surface vehicle. It travels through the ocean powered by wind and solar. We can send it communicates in two-way communications to our laptops via Iridium satellite, and we can send it waypoints to tell it where to go. It has a rigid sail that's 5 meters tall, and it can tack and go upwind and downwind, and it traced this trace across the Gulf Stream for 19 days. It was supposed to be a month, but on day 19, the Gulf Stream had other ideas for it, where 40-knot winds opposed a 5-knot current and built up a sea state of 12-meter significant wave height. So that's over 35 feet, significant wave height. And that was just too much for our 5-meter rigid wing. So at some point, a breaking wave crashed over the top of it and broke the sail off. And when it came up, it wasn't taking very good measurements. They did manage with the damaged sail to get it to Bermuda, where it was repaired and redeployed, and it's done great things since then. But for our purposes, we got 19 days of incredible data zigzagging across the Gulf Stream. The black lines in the background are sea surface temperature contours. So the dark black one kind of shows you the position of the Gulf Stream. So we did our best to zigzag across it, get all this CO2 data, and wrote a paper that kind of tried to use a pun that these autonomous observations reveal a perfect storm for ocean CO2 uptake. The perfect storm being that not the bad one that took out the sail drone, but the fact that the ocean is has very low CO2 at its surface near the Gulf Stream, and the atmosphere is pretty well mixed. So it has its background concentration, or a little bit more, because it's coming off the highly industrialized coastline of the eastern US. And so where the atmosphere has much higher CO2 than the ocean, the ocean wants to come into equilibrium. So the atmosphere is driving CO2 into the ocean. And then the winds, these strong winds, drive it in even faster by creating a frothy sea state that brings bubbles into the ocean, and also just increasing the air-sea exchange. So that was our 2019 effort. And despite the challenges we faced, we tried again in 2022 and 2023. I'm happy to report we still have 2 sail drones out there today. We did manage to damage another one, but the 2019 trace is shown in white. The pink traces are the pathways of the 3 sail drones that we started with in December 9th through March 9th. 2 are still going strong, but this is just the last time Sarah Nickford, my student, downloaded the data. So we have sail drones at 3 positions in the Gulf Stream, zigzagging across it. And collecting just a wealth of data that I'm sure will be analyzed, not just by us in the coming years, but by probably many groups looking at many different questions and challenges. This year, we decided to try to meet up with the sail drone with another autonomous vehicle called a sea glider. So the sail drone just provides a surface trace of data along the top of the ocean. It really just sees the top several 50 centimeters or so. But we can put another robot in. This is a glider. It's a torpedo-shaped instrument that collects all kinds of oceanographic variables beneath the ocean surface. It can dive to 1 kilometer below the ocean surface, and that's the deployment by another GSO student, Luis Pomales. It is driven by buoyancy. So it just has a pump that pumps oil in and out of a bladder. When the oil is in the bladder, it rises to the ocean surface. When the oil is sucked into the body of the glider, it sinks below the ocean surface. So it would just go up and down, but it has wings that channels that vertical motion into the horizontal. So it makes a sawtooth through the ocean. When it comes to the surface, it pops an antenna up. We again have two-way communications via satellite, and we can tell it where to go to the next waypoint. So now we have a sea glider in the ocean, kind of holding a position, and the sail drone zipping back and forth and meeting up with it. And in a couple of weeks, we'll be on the Endeavour, the research vessel Endeavour, to meet up with all these assets with a ship to validate their data and also take measurements at different scales and different rates. We'll also do some outreach with school kids deploying a mini boat that they created in one of the elementary schools, and various other activities. I'm working with a colleague at the Graduate School of Oceanography, my newest colleague, a chemical oceanographer named Hongji Wang. And so together and with a whole bunch of students, we're going to collect some great data and start to resolve the carbon sink at ever greater detail and with greater understanding of why the ocean's doing what it's doing and what we expect its stability or vulnerability to be in the future. We are not giving up at the Gulf Stream. In fact, my next project is to go work in the Arctic. I remember I mentioned David Ho from that tweet that I showed earlier. He's the lead investigator, and I'm a co-investigator on a project in the Arctic called Classy. And so this is a clever way that we teamed up with a group called SASSY. So it's Classy on SASSY. SASSY is a NASA-funded project called Salinity and Stratification at the Sea Ice Edge, a huge group of NASA scientists and other physical oceanographers. We're looking at how the melting of sea ice leaves a freshwater lens at the surface of the Arctic and can help predict the next winter's sea ice. I should get this animation started. If it will, let's see, I'll try one more time. This is an animation of the, doesn't want to play, so try one more time. There we go. So as many people know, the Arctic sea ice has been melting rapidly year on year. So this is from NASA satellites, the view of Arctic sea ice. And since microwave satellites were first launched in the 70s, we've seen sea ice in the Arctic go from a high of about 7 million square kilometers annual average to less than half of that in just about 40 years, 45 years. So these scientists from NASA that put the SASSY project together want to study the ice melt and freeze up, which is very important for navigation and lots of other things. But they were really focused on salinity, and we decided to add carbon. So we called it carbon levels at the salinity stratified sea ice edge. So we're Classy on SASSY, and we're going and adding. So this is a SASSY diagram showing all the assets they're going to deploy: ice buoys to the melting sea ice, a wave glider, which is another uncrewed surface vehicle powered not by wind energy, but by wave energy. And they're going out with a boat and drones and aircraft and all kinds of things. And we'll be there. We're sending a postdoc there to take carbon samples along the way, because when the sea ice melts, it leaves behind a freshwater puddle at the ocean surface that is very, very slowly mixed away. It can be there for up to a month after melting. And the exchange of CO2 across the surface of the Arctic is really mediated by the very most layer. And so if that freshwater puddle is there, it can really change how much CO2 the Arctic can absorb. And it goes totally unobserved because all of those ships that measure carbon dioxide at the surface that I showed you in that atlas do it at 5 meters, which is below those puddles, those freshwater puddles from the melting ice. So we hope to resolve that and get a better view of carbon levels in the Arctic. Ultimately, I'm part of a very big group called OASIS, which is the Observing Air-Sea Interaction Strategy. And so, Lao Tzu, when he wrote the Tao Te Ching, said, the journey of 1,000 miles starts with a single step. And as an oceanographer, I like to think that the journey to global coverage starts with some process studies. So my efforts in the Gulf Stream with Sail Drone and in the Arctic with Classy, as well as many of my colleagues' efforts in the Southern Ocean, the Mediterranean, and throughout the globe, are doing all these process studies, which ultimately we hope can become part of a global network to better resolve air-sea interactions. And not just for carbon, but also for heat and fresh water and momentum, which are the things that govern our weather forecasts. So we hope that over time, we can use these kinds of observations to improve weather forecasts and to improve our understanding of the ocean carbon sink. And this is a collective effort that's part of the United Nations Ocean Decade. So we hope by 2030, we really have a plan ready or even implemented for global coverage of these air-sea interactions. And again, I am happy to take any questions in the chat or Q&A at any time, because I'm moving on now from like the specifics of these process studies to kind of the bigger picture question that I touched on earlier, which is why it's so critical to close the global carbon budget. And I think to answer this question, it helps to revisit, or in this talk, visit for the first time, the goals that were set forward at the Paris Climate Summit as part of the Paris Climate Accord of how we want to limit global warming. And those goals were stated to limit global warming to well below 2 and preferably below 1.5 degrees Celsius compared to pre-industrial levels. And now, keeping in mind, we're already at 1 degree Celsius or 1.8 degrees Fahrenheit above pre-industrial levels. So we're kind of 2/3 of the way, unfortunately, to that stricter goal. And I can't emphasize enough that every 1/10 of a degree really matters. We don't blow past one goal and then stop pumping the brakes. We're trying to limit warming as much as possible. And after Paris was signed, scientists made a very big effort to evaluate the difference between 1.5 and 2 degrees in the future. And I thought this primer from Carbon Brief did a good job explaining the differences. And we have to remember that with even 1 degree Celsius, we're seeing stronger hurricanes already, heat waves and droughts on the West Coast that have been leading to destructive wildfires. Today in India and Pakistan, there's a heat wave ongoing. It's only April and temperatures there are soaring to between 110 to 115 degrees Fahrenheit. It's a reminder, to me, a very sobering reminder that those who have contributed the least to climate change, still in very energy poor regions of the world, suffer first and worst from the effects of climate change. And so it's really, I suspect that everyone on this call feels the same. It's really imperative to slow and stop global warming as much as possible. So under 1.5 degrees Celsius, we expect, 1.1 months of heat waves where it used to be a strong anomaly lasting single days. And under 2 degrees, that will be even 2 weeks longer. Fresh water, this is just an example in the Mediterranean, but a very highly populated region of the world, will be reduced by about 10% under a 1.5 degree world and about 20% under a 2 degree world. Heavy rainfall, something that afflicts the northeast of the US quite a bit. More of our rain falls in more concentrated downpours now. And I know that if you live on Aquidneck Island, you experience this as flooded streets. The streets were not designed to drain as quickly as they need to under the conditions of heavier downpours. We expect that to increase even another 5% under a 1.5 degree world and 7% under a 2 degree world. One reason I like this primer is because it's very, it's very fair. It shows that wheat and maize production will decrease under a 1.5 and 2 degree world, about 10% for wheat under 1.5 and 16% under a 2 degree world. But soy and rice do slightly better in the warmer climate. And it shows sea level rise and also coral bleaching. Sadly, corals are very much at risk. We've already had lots of massive bleaching of corals from warming and ocean acidification and other stressors. We think 90% of the reefs will be at risk from 2050 onward under 1.5 degree world, but there will be almost complete loss under a 2 degree world. So don't worry, I'm going to relate this back to the ocean carbon uptake that I was talking about earlier. What do we need to do to limit warming to 1.5 or 2 degrees? What we need to do is clear. We need to get to zero emissions as quickly as possible, and then try even harder to make that quicker. And so this is a plot of our global greenhouse gas emissions from 1990 to present in black, and then into the future in all these various projections. And so the black line shows the torrid pace of increase in CO2 emissions from the 1990s to about 2015. It was just rising so quickly. And then as a hopeful sign, 2015 to present has seen almost a plateauing of emissions. Some of that's from a change in land use, which got a bit better over that time. But some of that has been a slowdown, at least in the rate of increase. And so we hope that we have already reached peak emissions now, and that we're at peak, we're at the top of the mountain and looking down, and we just have to get now to net zero. And if you had asked even a few years ago where we were headed, most scientists pre-Paris thought we were on track for a 3.5 degree to 4.5 degree Celsius increase, which would be absolutely catastrophic. Current policies and actions already put us on a 2.5 to 2.9 degree path. So we no longer expect warming to exceed 3 degrees Celsius. That's great progress, but it's not nearly enough. 3 degrees Celsius is really still very bad. There are 2030 targets in place here to get us on an even better path than the policies and actions. So people have said they want to do better, and they have targets in place to do better than the policies and actions in place. And then there are some pledges and targets that go beyond 2030 that are even better and limit warming to 2.1 degrees, but they have yet to be accompanied by action and policies. And there's some optimistic scenarios out there that say we might limit warming to below 2 degrees based on economics alone, just that coal and oil and gas won't compete with renewables for long. But the scenario in which we really keep things below to 1.5 degrees Celsius or below requires extraordinary reduction in emissions, a halving of carbon emissions by 2030, 8 years to cut our current emissions in half, and getting to basically to net zero by 2050. And here the pathway really matters. CO2, once emitted to the atmosphere, stays in the atmosphere for hundreds to thousands of years. It only is lost from the atmosphere by absorption in the ocean or in the terrestrial biosphere, in land plants. There's no other way to get rid of it. So if we take a slow path to reduction, all of the CO2 between what we did and what we wished we did will still be in the atmosphere, unless we find a way to suck it out of the atmosphere. Okay, and then one more thing, those 1.5 degree pathway, oops, sorry, went in the wrong direction. The 1.5 degree pathway, that's just meant for these eyes to show up, requires that our emissions go below zero. Negative emissions, what is that? That means humans have found a way to suck CO2 out of the atmosphere. All of these reductions that from emissions being high to lower, we know how to do much of that. I would say 50 to 80%, and there's various estimates. We know how to decarbonize the electricity grid to make it fully running on wind, solar, geothermal, and nuclear, and having more storage. We know how to electrify transport, cars, and we know how to reduce the car miles driven through public transportation and more accessible bike paths and urban pedestrian lanes. We know there are agricultural solutions for more sustainable farming and to eat less red meat, which can reduce methane emissions, which are a very strong lever in our climate system, as well as CO2. But no matter how much we reduce emissions, even if we miraculously have them by 2030 and reduce nearly to zero by 2050, there will be a need to remove carbon from the atmosphere. I think this is a little appreciated conclusion from the Intergovernmental Panel on Climate Change's climate report that came out last year. And I need to emphasize in the strongest possible language that pulling CO2 out of the atmosphere is something we do not know how to do at scale. And it is always, carbon dioxide removed from the atmosphere is always subordinate to not emitting the CO2 in the first place, because we don't have that tech yet. Where we know how to reduce emissions, we don't know how to pull CO2 out of the atmosphere at scale. And yet we need research to figure out if we will ever be able to do that. So Cameron Little, I'm so glad, asked, are there viable CO2 reduction technologies being developed? There's research and ever more funding for it. So the biggest funding for this if you had asked me a year ago, was about $10 million, or a couple of years ago. A big climate fund by Stripe, the credit card company, and lots of others just funded a $995 million, so nearly $1 billion, to accelerate research into carbon dioxide removal. But right now, the biggest carbon dioxide removal facility in the world is called Orca in Iceland, and it removes a whopping 4,000 tons of CO2 per year. This y-axis is in billion tons per year, 40 billion tons per year. So if we thought of the Orca plant as a time machine that pulled us backwards in time to removing CO2 from the atmosphere, it would reverse time worth of 3 seconds worth of emissions. So 4,000, if it ran at top capacity for a full year, it would remove as much emissions as we are currently emitting in every 3 seconds. So this is not at scale yet. It needs to scale by a factor of 10,000 to become the scale that we wish it to have. And it stores that CO2 in geological reservoirs underground. It has to be durable too, that removal. Another technology is a little bit lower tech. It's called tree planting, and it's a favorite of people who want to look for solutions. The best estimates I can find for that is if you planted trees on most of the available land surface and allowed them to grow, and they didn't go up in smoke from wildfires and things of that nature, it would reverse up to 6 years of emissions at their current rate. And that's all we get if we plant all the land and allow the forest to grow to 2100 and nothing happens to hurt them. So we really need other solutions. And that's where oceanographers are starting to have become popular people to guide the community on whether the oceans could serve some of this purpose. Remember, they cover 70% of the Earth's surface and have stored more CO2 in the past than they are currently. So the National Academy of Sciences did a recent report, 2021, looking at a research strategy for ocean-based carbon dioxide removal and sequestration, looking at various possibilities, electrochemical, kelp farming, which is very popularly researched in Maine, and ocean alkalinity enhancement, which I think could be a positive motion in general because it also fights ocean acidification. But we're really in the infancy of figuring out if any of these things can be viable. And the science is really needed to figure out whether any of these are viable and also verify if they work. So I told you I would come back to the ocean carbon and measuring it and knowing what it is. If we're going to gigaton uptake of CO2, we really need to close the global carbon budget to figure out if it's working, right? We need independent ways to measure and verify these efforts. And if some of that CO2 is going to go into the ocean, humans are going to manipulate it to get it into the ocean, which may not be a good idea, but is something that is now being actively researched. It's essential that we verify the success or failure of any purported carbon dioxide removal efforts. Because if we can do it in a responsible way that has less harm than the global warming that would result from not doing it, it would be nice to know that. But it's also critical that we know if we think we're doing it and it's not succeeding, that we don't count it against our emissions, because we have to get to net zero ultimately. And so I'm going to end with just a quote from Bina Venkataraman, who wrote The Optimist Telescope and was the former opinion editor for the Globe. I went into oceanography thinking I would have a crystal ball into the future. And what I've learned is that is embodied in this quote, is that we really don't know what the future holds, only that we can change it. So I have developed some insights into how the Earth system works and how it reacts to different perturbations, but I don't know how humans will act in the future. And so I think it's so great to have this lecture series and have you all listening, because the more we engage on climate change, act both as individuals and in the collective, make sure the people who represent us at the local, state, and federal levels know that we vote on climate issues and care about them, then that's what can change the future, can reduce our emissions, and get the research started to understand if carbon removal will be a possibility in the future. And so with that, I just want to thank you for listening and your patience, and also again to William Donner for putting together this important series. Thanks. And I'm happy to take any questions. Okay, so I have a question in from Norman McLeod, who asked if I've had success talking with climate change deniers about this. And I think that's pretty interesting. So I don't encounter too many climate change deniers. I have had a couple in my class. I teach a class on climate change, very few, maybe like two. And we start with the science, no politics. We just start with what CO2 is. It's a molecule with a carbon at the center and two oxygens, right? And you can see that if it encounters the radiation that leaves the surface of the earth, it vibrates. And when it vibrates, that's heat. And so we start from like that simple thing and build from there, which has been known since the 1800s. And we build from there to understand why releasing greenhouse gases into the atmosphere changes our climate. And so by the time we get to the consequences and the solutions, there's no, it's kind of like if someone says, do you believe in climate change? I say, do you believe in gravity? It's just the science on the causes of climate change and the fact that it's changing is just irrefutable. And that is very persuasive to those students. What's a harder problem, and so thank you for this question, is the defeatism, where people say, you know, especially students, I feel sad for students that say it's end times, there's nothing we can do, and throw their hands up. There's no way to get around this, because that's a different form of denialism. It's a denial that there are solutions, and there are. There's no doubt in my mind that we could mobilize to have to cut our emissions in half by 2030. The solution, I mean, the solutions are right there. We have states, Texas gets, I think, 40% of its energy, or 50. I just looked at this yesterday, from renewables, mostly wind. We have, I think, 13 states getting over 40% of their electricity from renewables. So it's the cheapest form of energy there is now. And China, which is the biggest emitter, is doing a ton of not only research and less research, but more implementation of wind and solar and electrified transport. So, and it's the other thing that people don't tend to relate, don't always realize, is that there are so many health benefits to removing fossil fuels. So even if you didn't care about climate change at all, we lose, the estimates are that there's millions of lives lost prematurely from the particulates that go in the atmosphere that affect cardiovascular health. I think over 1 million every year in India alone of premature death from cardiovascular disease associated with particulates from the burning of fossil fuels, unrelated to climate change, or just from the same source, fossil fuels. But and so there are so many reasons to change, to rapidly reduce our dependence on fossil fuels. So that was a long-winded answer, but you're the only question on the board, so I had time. Are there other thoughts or questions? I don't see any. I am, and we've been on about 45 minutes. I don't know. Oh, there we go. I have heard that about 2% of GDP would deal with this. I have heard that number too. And I haven't examined it. Like, I haven't looked at it with a critical eye, but I have seen that figure. And I think it's believable. So I mean, I've seen it from credible sources. They say that the mobilization to fight World War II was nearly 10% of GDP, and that wherever I read that number, that 2% could do it. And here's something that I followed pretty closely that's really relevant for present day and also advocacy, if you're into that kind of thing. The Build Back Better Act had climate provisions. Of course, it was a giant bill that had lots of different things in it, but the climate piece of it was about $500 billion, which is much less than 2% of GDP. And a modeler at Princeton who models economics and policies and energy, his name's Jesse Jenkins. He's also a great Twitter follow. he ran the Build Back Better provisions through his model and found that it would be enough to hit our climate goals as laid out in Paris, which are consistent with a 2-degree world. Of course, that's just the US policy. We'd rely on that kind of leadership also existing in other countries. So that's a lot of ifs. So that 500 billion was enough for the US to hit its 2030 targets, which themselves are consistent with the 2-degree goals. It's the short-term piece of that trajectory. Thanks, Norman. Oh, are there potential negative impacts of increasing the level of CO2 in the ocean? Yes, is the short answer, but it really depends so much. So this is a question from Steve Hannaberry. It really depends so much on the technique. So I think there are a few techniques that have no downside, right? Like one of the techniques we think might store more carbon is ecosystem restoration. So like destroyed salt marshes, destroyed mangroves, bringing them back and restoring them to their full health. It's just not clear that will have a major scalable impact on CO2, but there's no downside, right? If we wrecked ecosystem when we restore it. There are others that have more risk associated with them. Even kelp farming, we don't totally know what it would do to the ecosystems because we're talking about billion-ton scale is the goal. So we want to be really careful not to, create oxygen dead zones as the kelp decays, for instance. And so none of the scientists that I know of are actually proposing to do anything at scale. Most of them aren't even really doing, there's some kelp farming because that's already a kind of a known quantity. People have been doing it for as a food source for, hundreds, if not thousands of years in Asia, but now more and more in the US. But to do it at a gigaton scale, and then the idea is to sink that kelp, because if we eat it and it's just still active in the climate system. So some have more risk than others. The other one I find hard to find a downside, although you can't rule it out, and we need to do intense study to know, is ocean alkalinization. It's basically offsetting the acidity. So we've acidified the oceans because as they take up CO2, they become more acidic. We could add alkalinity now, like the way you lime your garden or your lawn. You can add lime to the ocean, and that lowers the acidity and also allows the ocean to take up more CO2. It could influence the phytoplankton and have negative consequences that way. And so that's really important to look at. But there are ways of doing it with electrochemical methods that at least the models would suggest they are unlikely to be super harmful. And remember, we always have to weigh the harms of the technique against the harms of the unmitigated climate change. So I think but that's a great question, and one that, of course, is at the forefront of any scientist studying it. Okay, and then Sam Berger in the Q&A in a separate place has asked, will governments survive the mass migrations which are bound to follow crop failures due to climate change, or am I way too pessimistic? Oh my gosh, I have to remind you that I'm an oceanographer, and I don't know, I don't know what will happen with migrations and all of those politics. I have 2 children, elementary age children, and I don't want them to live in a world where crop failures and mass migrations become the norm. And so all I can say is, I don't know what the future holds. I only know that we can change it. And I want to work to change it. And I hope that my work helps to that. And I hope that it gives me a sense of hope when I see other people working towards that as well. I think there's already climate migrants. I think that much is true. And I just hope it doesn't get much worse. And so, there are simple things we can do as individuals. Like there's a group called Science Moms that have made swap it one of their mottos. So if you have a car that works and you're not ready to change it, that's one thing. But if you're about to change your car, think about buying electric. If you're about to change your stove, don't replace a gas stove with a gas stove. Think about going to induction or electric. and that's good for your health. The indoor air quality associated with gas ranges is not great. And we think that we like cooking on it better, but is it really that much better? I mean, so there are things we can do as individuals, but then we can also like advocate for better climate solutions, for Build Back Better, for instance, or the climate components of Build Back Better. If you don't like the other components, I'm not gonna. So we just keep doing our best is, I guess, my answer. Keep talking about it, keep it front of mind. Oh, okay, I see. Cindy Havron has asked, how could there possibly be enough lime to impact the alkalinity of the ocean? Also a very excellent question. You would be surprised. So I've looked into this a little bit. The modern production of lime for agricultural use is a 0.5 gigaton. And the way it scales is like, if you use a gigaton of lime is almost a gigaton of CO2. So that's the lime just currently used for agriculture. You could imagine that industry, there is a lot. Basically, if that industry doubled, that's a 0.5 gigaton per year is sold for agricultural purposes. If that were to double, that could be a 0.5 gigaton. It is not the whole solution. It never can be, always subordinate to emissions reductions. But there is like gigaton capacity. And then the electrochemical methods, I hope I can get this right. I'm a physical oceanographer, so I'm always a little on edge describing chemistry. But the idea is that you could split water at the ocean surface where the acidification has happened most rapidly. The split water would produce H+ ions, that's the acidity, and OH, which is the alkalinity. If you could somehow pump the H+ ions and distribute it over the 4 to 6 kilometers of ocean depth, it would be negligibly influencing the ocean depth, because if you could distribute it like through a pipe with a leaky pipe, an intentionally leaky pipe, then we'd take the acidity that is already collected at the ocean surface, distributed throughout the ocean interior. The OH molecules left behind provide alkalinity, and then that would help to shift the alkalinity of the surface to a place both that counters ocean acidification and also to take up CO2. So that's an alkalinization method that doesn't rely on grinding rocks, and it's interesting. I don't know if it would work either. And I think this is in its infancy, which is why I always say emissions reductions first and foremost right away as fast as possible, and then research on this as is acutely needed. And we're actually, a group I'm part of is bringing a workshop to think through the pitfalls and promises and of these methods, and how the science community can figure out, whether this is at all feasible or harmful, and all of those things. And okay, Martha Curley. How can we entice private businesses to invest in carbon reduction? These are really tough questions. Again, I'm an oceanographer, so this is like, I think about these things a lot, so I can give you a personal opinion, but it's not informed the way an ocean question might be. First of all, some businesses are doing a lot. Microsoft has a program to reduce its emissions to 0 and then remove from the atmosphere its historical emissions. So it wants to get its current operations to no carbon emissions, and then reduce it, and then pull CO2 out of the atmosphere through reforestation or direct air capture, like that Orca plant in Iceland, to remove its historical emissions. And it's not all greenwashing. So the person who's in charge of verifying if that's working is someone I went to graduate school with. So and he's written some really interesting papers of how they verified it. And I think they got proposals of carbon removal from, I don't know, hundreds, many sources. And they, I think, said that only a few % of them were credible. So they are being discerning in what they're saying is real. So that's just, I don't know what made them want to do that, except maybe their public image, or maybe someone at the top cares. I don't know. Google is trying to reduce its emissions to zero, and not over an annual mean, but 24/7. So every hour of every day is replaced by wind, solar, geothermal storage. That's a much, much harder problem because, as we know, the wind doesn't always blow and the sun doesn't always shine. So having 24/7 zero emissions is a much harder problem. But if Google takes that on and does the R&D on that, then it will help accelerate that in the future when we want the whole grid to be renewables and renewables, nuclear, and storage. So why did Google do that? Again, I don't know what enticed them except public image or someone at the top that cares. And so the more people know that we care, the better. Yeah, I don't know. That's all I can think of to say. So, yeah, anyone else? I think I've kept you listening to my voice for almost an hour. So maybe people are tiring out and ready for dinner. But it was really excellent to be here with you. And I don't know if, yeah, thank you. You can call me Jamie. And I'm always happy to do these kinds of things. Actually, I've been to 2 high schools and I hope to go to a 3rd in September through this program. And so it's just a real honor to talk to people who care, that want to learn more and work towards solutions. Thanks, Peter. Okay. So Laura, yeah, thanks everyone. Laura, Emily, and the Aquidneck Land Trust people, thank you for setting this up and doing all the tech support. And again, William Donner for sponsoring it. And I don't know if I'm responsible for closing this out. But I've really enjoyed the Donner series and appreciate your time.
Thank you so much for being here. It looks like our ALT team has dropped, but we do appreciate your time this evening and your wonderful presentation.
Thank you so much. Okay, take care.
Thank you.